Let x and y be bounded infinite sequences. Prove that the set containing the absolute value of the difference between x1 and y1, the absolute value of the difference between x2 and y2, and so on, is bounded. Now, in a previous video, we've talked about that if a subset of a metric space is bounded, then it is contained in an open or closed ball. And we've proved in that video that it is contained in an open and closed ball with center P in that metric space E for any P and E. For any P and E. So, for any P and E where our E is our metric space. So, since in this particular problem, we're talking about the metric R, and we can use the standard metric that you usually define on R, which is the absolute value between any two elements where A and B is in R. So that this is a metric that satisfies all four of the metric space properties, and is the usual metric that we define on the real numbers. So we can say the following. We know by the proof that we did in the previous video that there exists a closed ball with center A in R for any A in R. So there exists a closed ball. There exists a closed ball with center A in R for any A in R that contains X. So we can say that since this is valid for any A in R, we can say that there exists a closed ball, and we don't know the radius, so we don't know what the specific radius is, but since we know that there exists a closed ball and it must have some radius, then we'll just call that radius M with radius M, and center 0. Remember, we've proven in that separate video that we can have, if a set is bounded, then for any A in that metric space of which that set exists in, and of which that set is bounded in, then for any A in that metric space, there exists a closed ball with that center A that contains that bounded set. So we can say the following: there exists a closed ball with radius M and center 0 that contains X, our sequence X, which is equal to, as they said, X1, X2, X3, and so on. Okay, so we can say if this sequence is contained in the closed ball with radius M and center 0, then that implies that xi for any, or I should say, for any I in the natural numbers, because this is how we index sequences, by the natural numbers 1, 2, 3, 4, and so on. For any I in the natural numbers, xi is in the set all A such that 0 minus A, the absolute value of 0 minus A, which is our metric. Well, let me go back one step. The distance between 0 and A is less than or equal to M, which is our radius of our closed ball. So this is our closed ball. This is our closed ball with radius M. This is the set that defines our closed ball with radius M, and this is equal to all A such that, and since the distance is defined as the absolute value of 0 minus A, and the 0, again, our center is 0, and any arbitrary point in that closed ball A, the distance between our center 0 and any arbitrary point in that closed ball A must be less than or equal to the radius of that closed ball. So this is less than or equal to M, and again, this is equal to all A such that A, the absolute value of A, is strictly less than M. So we can say the following: the absolute value of xi is less than or equal to M for some M. And we can say the same thing for our sequence y. By the same argument, yi is less than or equal to for some n. So xi is less than or equal to M for some M, and yi is less than or equal to n for some n. And so check this out. We're almost done. We've almost proven what we wanted to prove. That is, we've almost proven that this set right here is bounded. And I'll show you how we were almost proven that. So check this out. If xi is less than or equal to M, then we can say the following: xi, if and this is for all I, this is for all I, if xi, we have three possibilities for xi. If xi is positive, then that means that negative xi is negative, obviously. So the negative of xi is less than 0. So therefore, it is strictly less than our positive xi, that is to say, xi is positive. I'm going to write here in the bottom, xi is strictly greater than 0. So therefore, negative xi is strictly less than this xi, which is equal to xi, which is less than or equal to m. And you might be wondering why I'm doing this, and it'll become clearer later on. If xi is equal to 0, then that implies negative xi is equal to xi, which is equal to the absolute value of xi, which is less than or equal to m. And we can also say that if xi is less than or 0, that is to say that xi is negative, then xi, which is xi, if xi is less than 0, xi is going to be less than negative xi, which is going to be a positive number, which is going to be strictly greater than 0, which is equal to the absolute value of xi, because xi, if xi is negative by definition of absolute value, then the absolute value of xi is going to be -1 times xi. And remember, for all I, the absolute value of xi is less than or equal to m. And we can say the same statements, for yi, and I won't write them here, but this allows us to say the following. Negative xi is less than or equal to m for all I, and positive xi is less than or equal to m for all I. And we can say the same thing for yi's. So negative yi, the negative of yi is less than or equal to m, in for all I, and yi, by the same argument that we used above here, positive yi, the positive 1 times yi is less than or equal to n, for all I. So therefore, check out this. We've used this property multiple times over the course of our videos on metaphor math. We can say the following. Remember this property. A is less than or equal to B, and C is less than or equal to D. Then that implies together that A plus C is less than or equal to B plus D. And I have a video proving that if A is strictly less than B and C is less than or equal to D, then that implies together that A plus C is strictly less than B plus D. And the proof for this extends very nicely to the proof for this property here. And look at what we have here. We have that since xi is less than m and negative yi is less than or equal, xi is less than or equal to m and negative y is less than or equal to n, then xi, let me change colors here, xi plus negative yi, which is equal to xi minus yi, is less than or equal to m plus n. And we can say the same thing going in a different way. Yi, since yi is less than or equal to n and negative xi is less than or equal to m, then yi plus negative xi, which is equal to yi minus xi, is less than or equal to n plus m. So look at this. I've proven in a separate video that if we have some a minus b is strictly less than epsilon, and b minus a is strictly less than epsilon, and we can extend this very easily to less than or equal to, then this together implies that the absolute value of a minus b is strictly less than epsilon. And again, I've proven this in a separate video. I'll link all my separate video proofs in the description and also in the eye icon in the top right corner. So we can say the following. The absolute value of xi minus yi is less than or equal to m plus n. And look at this. We've just shown that it's bounded from above. Namely, that it's bounded from above by m plus n. And it's bounded from below by 0, obviously, because the absolute value of any real number is strictly greater than or equal to 0. So therefore, it must be bounded, and we're finished.